Let's look at the solution of number system bytes. For how many values of n being a natural number less than 15, would the remainder when nm divided by 12 never be 1, where m could be any natural number? Okay, so I know n is limited. N has to be a natural number less than 15, and m could be anything. So I'm going, let us take all those cases. Either you have m by 12, or you have 2m by 12, or you have 3m by 12, or you have 4m by 12, 5m by 12, 6m by 12, 7m by 12, 8m by 12, 9m by 12, 10m by 12, 11m by 12, 12m by 12, 13m by 12, and 14m by 12. This is what we are dealing with. These are the 14 cases. Now see, m by 12. M can take any value. Can you get a remainder 1 here sometime? Can you get a remainder here? 1? Yes, if I take m equal to 1 itself, if I take m equal to 1 itself, I can get a remainder 1. And our objective is that remainder should never be 1. This is out of the running. Now 2 into some number divided by 12. Can you see the number at the top will necessarily be even? If I divide an even number by an even number, the remainder will always be even. So can I ever get a remainder 1? No. So this case should be counted. Similarly, the numerator here is a multiple of 3. Denominator is also a multiple of 3. Regardless of what value you take of m, your remainder will always be a multiple of 3. And therefore, you can never get remainder 1 here. This should also be counted. In this case, the remainder will always be a multiple of 4. This case should be counted. In this case, because 5 and 12 are co-prime, remainder 1 is possible. Let's say you take the value of m as 5 itself, 5 into 5, 25, with remainder, with upon division by 12, it will give remainder 1. So this case has to be eliminated. Here, the remainder will necessarily be a multiple of 6, so you can never get 1. This case will get counted. 7 into something divided by 12, as good as 7 into 7, hopefully you can see. So this case should not be counted. 8 and 12, the remainder will necessarily be a multiple of 4. 9 and 12, remainder will necessarily be a multiple of 3. 10 and 12, remainder will necessarily be a multiple of 2. So these 3 cases should be counted. 11 and 12 are co-prime. So 11 into 11 is 121, can give a remainder of 1 with 12. This should not be counted. A multiple of 12 divided by 12, remainder is always 0. You will never get 1. So this should be counted. 13 into m divided by 12. If I take m equal to 1, I can get remainder 1. This is gone. Here 14 and 12, because the common number HCF is 2, the remainder will always be a multiple of 2. Basically, what this question was asking you, if you can pay attention, basically what this question was asking you was, how many numbers up till 14 are co-prime with 12? If you can see, the cases that we have removed are numbers that are co-prime with 12. These are the only cases we have removed. These 5 cases we have removed. From 14, when you remove 5, how many cases are you left with? 9. Answer should be 9. Even if you don't know the co-prime wala interpretation, you can actually do this by listing out every possible case and then seeing if remainder 1 is possible or not. Next one, it is given that a into 10 raised to the power b is equal to 42 raised to the power 105 into 75 raised to the power 48, where a and b are natural numbers and a is not a multiple of 10, which means all the 10s that are getting created on the RHS are consumed within this expression 10 raised to the power b. What is the unit digit of a? Okay, so the number was a into 10 raised to the power b, which was 21 raised to the power 105 into 2 raised to the power 105 into 3 raised to the power 48 into 5 raised to the power 96. This was 25 raised to the power 48 or 5 raised to the power 96, seedha doubled. Now, because all 10s go in this expression, can I get 10 raised to the power b would have 2 raised to the power 96 into 5 raised to the power 96. Basically, b will turn out to be 96. This is known. All possible 10s that can be used up are used up. So A will turn out to be 21 raised to the power 105 into 2 raised to the power 9 into 3 raised to the power 48. And we only need the unit digit of this expression. 21 raised to any power, unit digit is always 1. 2 raised to the power 9 is as good as 2 raised to the power 1, so unit digit is 2. 3 raised to the power 48 is as good as 3 raised to the power 4, so unit digit is 1. So unit digit of A will turn out to be 2. Answer to the question is 2. Next, how many natural numbers between 1 and 600, both inclusive, are not divisible by 9, but leave a remainder of 4 when divided by 5? Okay, so let's see. Let's look at a series. We've got 5n plus 4 kind of number. 5n plus 4 kind of number. How many numbers will there be 5n plus 4 kind of numbers from 1 to 600? From 1 to 600. The series will start at 4 and will keep going till 599. Counting how many numbers here, you can do that via AP, or if you can see, this is nothing but a table of 5. All you need to do is add 1 everywhere. You will see that these are 120 terms. These are 120 terms. But from this list, I have to remove all multiples of 9. From this list, I have to remove all multiples of 9. First multiple of 9, of course, 9 is involved. Can you see the next number in the list? The gap between these two, will be a multiple of 9. And because n is a part of this series, it will also be a multiple of 5. So can I say, once I've identified 9, the next number that I have to remove will be obtained by adding 45 to it, a multiple of 9 and a multiple of 5. So the next number that gets removed is 54. The next number that gets removed is 99. Next number that gets removed is 144. Next number that gets removed is 189. So on and so forth, we keep going. In fact, within this series, hopefully you can see the series that we are looking at is 45n plus 9. The series that we are removing is 45n plus 9. Yes. So now in the range 1 to 600, hopefully you can see the last number of the type 45n plus 9 will be 594. Will be 594. If you can break it down, how I am reaching there is 450, 135 and 9. Multiple of 45, multiple of 45 and 9, 594. We simply need to remove the numbers in this series. However many numbers we are getting in this series to get to our final answer. 120 was the total sample space. From these, unacceptable terms have to be removed. So let's see, 594, 9 to 594. This is a table of 45. So if I add 36 everywhere, this turns to 45. This will turn to 630. So 630 divided by 45 I want to do now. So cancel 1, 180. So 4. 14 terms are present in this unacceptable series. 14 terms are present within this unacceptable series. Others may choose to go down this path. A is equal to 9, D is equal to 45. So 594 is equal to 9 plus n minus 1 into 45. And then you can reach your n equal to 14. That is also acceptable. From 120 terms, 14 have to be removed. So the final answer to the question will be 106. Next question. If the HCF of two natural numbers is 8 and the difference of these two natural numbers is also 8, then find the greatest possible value of the larger of the two numbers if LCM of these two natural numbers is a 3-digit number. Okay, I'm saying let the first number be A, the second number be A. 8A, and the next number will be 8 times A plus 1, because the difference between them is also 8. The difference between them is also 8. And we know A and A plus 1, two consecutive numbers are always co-prime. So can I say their LCM will be equal to 8 into A plus 1? 8 into a plus 1, and we are told that the greatest possible value of the larger of these two LCM, if the LCM is a 3-digit number, if the LCM is a 3-digit number, this expression should be less than 1000, or a into a plus 1 should be less than 125. Or now you simply have to plug in the value of a to see. If you went 10 into 11, it is fine, 110. If you went 11 into 12, it is 132. It is not fine. So the pair that we are looking for is 10 and 11 only. So A will turn out to be 80, B will turn out to be 88. What the question asked me was, then find the greatest possible value of the larger of these two numbers. The greatest possible value is 88. Answer will be option C, 88. Next question. If 0.3636 dot into A and 0.3636 dot into B is equal to 0.5454 dot into C, where A, B, C are positive integers and C is an even multiple of 15, how many ordered triplets A, B, C are possible when the value of C is minimum? Okay, what I expect and want you to know is you should know these numbers. As soon as you see these numbers, a bulb should go off in your head. The expression is essentially 4 by 11A plus 4 by 11B is equal to 6 by 11C. This is what this is what should go off in your head instantly. This is what should go off in your head instantly. Okay. Now, it says C is an even multiple of 15. About C, C is an even multiple. So it is a multiple of 2. It is a multiple of 15. And from this expression, can you also see C is a multiple of 11? C is a multiple of 11. So if C is a multiple of 11, if C is a multiple of 11, why do I care if it is a multiple of 11? Does it necessarily, can't this be in decibels? No, it is not necessarily a multiple of 11. So let C be equal to 30. If it is an even number and it is 15, let it be 30. So I now have 4 by 11 plus 4 by 11. In fact, I can straight away write the LHS as 4 by 11 A plus B is equal to 6 by 11 into 30. So 11 and 11 gone. Now I'm left with 4 times A plus B is 6 into 30. Can I simply write it as A plus B is equal to 45? I've got my final expression. A plus B is indeed equal to 45. And if A plus B is equal to 45, and both of them are positive integers, the cases will range from 144 and will keep going till 44-1. So how many ordered triplets are possible? We will have 44 solution sets here, and in each of these cases, C will still be equal to 30 only. So how many solution sets are possible? Answer is option C, 44. That will be all for these set of questions. Hopefully you learned something. Okay, bye.